Hi guys, tonight we're going to explore one of the most mind-bending ideas in all of cosmology. What if our entire universe, everything we can see and touch and measure, exists inside a black hole? What if the Big Bang was actually the moment when matter collapsed into a cosmic black hole in some higher dimensional reality? If you enjoy these reality-warping sleep stories that challenge everything we think we know about existence, hit that like button and subscribe for more. And drop a comment letting me know what time it is, where you are, and where you're listening from. I love hearing from all you fellow night owls around the world. Alright, let's begin. Picture this. Right now, as you listen to these words, you might be sitting inside the most massive object imaginable, trapped beyond an event horizon so vast that light itself cannot escape. The coffee cup on your table, the air you breathe, the stars twinkling in the night sky, even the galaxies spiraling through space billions of light years away. All of it existing within the belly of a cosmic leviathan that defies our most fundamental understanding of reality. This isn't science fiction. It's a legitimate scientific hypothesis that suggests our entire observable universe, stretching 93 billion light-years across and containing over 2 trillion galaxies, each with hundreds of billions of stars, might be nothing more than the interior of a black hole in some higher dimensional space. The idea sounds preposterous at first. After all, we've been taught that black holes are cosmic vacuum cleaners, regions where gravity has become so intense that nothing can escape once it crosses the point of no return. We imagine them as dark, empty voids scattered throughout space, gobbling up matter and light with insatiable hunger. The supermassive black hole at the centre of our own Milky Way galaxy, Sagittarius A star, weighs in at approximately 4.3 million times the mass of our Sun, yet spans only about 24 million kilometers across, roughly the distance from Earth to Venus. How could something so compact contain the incomprehensible vastness of everything we know? The answer lies in a radical reimagining of what black holes actually are and how they behave according to the strange mathematics of Einstein's general relativity. When we peer into the equations that govern spacetime, we discover that the interior of a black hole isn't necessarily the crushing singularity of infinite density that popular science often portrays. Instead, it might be a region of expanding space that looks remarkably similar to our own universe. This hypothesis, known as the black hole cosmology model, or the Schwarzschild cosmology, suggests that what we perceive as the Big Bang, that moment 13.8 billion years ago, when space and time began expanding from an infinitesimally small point, was actually the moment when matter collapsed into a black hole in a higher dimensional parent universe. To understand how this could work, imagine standing at the edge of a waterfall, watching the cascade plunge into a misty abyss below. From your vantage point, you can see the water accelerating as it approaches the edge, moving faster and faster until it disappears from view. Now, imagine you're a fish swimming in that water. As you approach the waterfall's edge, you don't experience any particular moment of transition. You simply continue swimming forward, carried by the current into what lies beyond. This analogy captures something crucial about black hole event horizons. What appears to be a dramatic boundary from the outside might be completely unremarkable to someone passing through it. When astronomers calculate the critical density required for our universe to be geometrically flat, a measurement that comes in at approximately 9.4 times 10 to the negative 30th grams per cubic centimetre, they arrive at a number that's eerily similar to the density you'd find inside the event horizon of a black hole, with the mass and size of our observable universe. This isn't just a curious coincidence. If you were to calculate the Schwarzschild radius for an object with the mass of all the matter and energy in our observable universe, approximately 10 to the 53rd kilograms, you'd get a radius of roughly 46.5 billion light-years, which is strikingly close to the actual radius of the observable universe. The mathematics become even more intriguing when you consider the expansion rate of our universe, quantified by the Hubble constant at approximately 67.4 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years of distance, space itself is expanding at nearly 67.5 kilometers per second. At the edge of our observable universe, objects are receding from us at nearly the speed of light, approximately 300 million meters per second. This creates a natural boundary beyond which we cannot see, not because of any physical barrier, but because light from those regions can never reach us due to the expansion of space itself. This expansion bears a remarkable resemblance to what theoretical physics predicts should happen inside a black hole. Once matter crosses the event horizon, it doesn't immediately crash into a central singularity. Instead, it enters a region where space and time become severely warped. The traditional view suggests that all matter eventually reaches a point of infinite density at the center, but newer models propose that quantum effects might prevent this collapse, creating instead a region of expanding space that could theoretically support the existence of matter, energy, stars, planets, and even life. Consider what this means for our cosmic origin story. The Big Bang, as we understand it, describes the universe emerging from a state of infinite density and temperature, a singularity that physics cannot adequately explain. We know that in the first 380,000 years after the Big Bang, the universe was so hot and dense that atoms couldn't form, creating an opaque plasma that blocked light from traveling freely. The cosmic microwave background radiation we observe today, at a nearly uniform temperature of 2.7 Kelvin, with tiny fluctuations of only a few hundred microkelvin, represents the afterglow of this primordial fireball. But what if this wasn't the beginning of everything? What if it was simply the moment when matter in a parent universe collapsed past the point of no return, creating the expanding space we call home? This would explain why the cosmic microwave background appears so remarkably uniform across the entire sky, with temperature variations of less than 1 part in 100,000. In traditional Big Bang cosmology, this uniformity requires a period of exponential expansion called inflation, during which space expanded faster than light for a brief moment, smoothing out any initial irregularities. The black hole cosmology model could potentially explain this uniformity without requiring such an exotic inflationary period. The implications extend far beyond cosmology into the realm of fundamental physics. One of the most perplexing problems in modern science is the hierarchy problem, the vast difference between the strength of gravity and the other fundamental forces. Gravity is approximately 10 to the 39th power times weaker than electromagnetism, a discrepancy so enormous that it suggests something fundamental about the structure of reality that we don't yet understand. Some theories propose that gravity appears weak because it leaks into extra dimensions, spreading its influence across higher dimensional space, while the other forces remain confined to our familiar three-dimensional realm. If our universe exists inside a black hole in a higher dimensional space, it could explain why gravity seems so weak compared to other forces. The gravitational field we experience might be just a shadow of much stronger gravitational forces operating in the full, higher dimensional reality. This would mean that the fundamental constants we measure, the speed of light at exactly 299,792,458 meters per second, Planck's constant at 6.626 times 10 to the negative 34 joule seconds, and the gravitational constant at 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared, might not be truly fundamental at all, but rather emergent properties of our particular location within a vast multidimensional cosmos. The concept becomes even more mind-bending when you consider the possibility of nested universes, black holes within black holes, creating an infinite hierarchy of cosmic structures. Every black hole in our universe, from the stellar mass remnants created by supernovae to the supermassive giants lurking at galactic centers, might contain entire universes teeming with their own galaxies, stars, planets, and potentially life. The black hole at the center of the Andromeda Galaxy, weighing in at approximately 100 million solar masses with an event horizon spanning roughly 300 million kilometers, could house a universe filled with billions of galaxies, each containing billions of stars and potentially countless worlds. This nesting could extend infinitely in both directions. Just as our universe might exist inside a black hole in a parent universe, that parent universe might itself exist within an even larger black hole in an even more encompassing reality. The numbers become staggering when you try to contemplate the full implications. If each universe contains roughly 10 to the 80 atoms, and each universe spawns multiple black holes that create new universes, the total number of atoms across all nested realities quickly approaches infinity. Such a scenario would revolutionize our understanding of what we mean by everything. The observable universe, with its 2 trillion galaxies each containing an average of 100 billion stars, would represent just the tiniest fraction of a vast multidimensional reality. The Milky Way, our home galaxy stretching 100,000 light-years across and containing approximately 400 billion stars, would be nothing more than a microscopic speck within a cosmic structure so vast that our minds can barely begin to grasp its scale. The idea also raises profound questions about the nature of time and causality. Inside a black hole, the normal relationship between space and time becomes inverted. In our everyday experience, we can move freely through space but are dragged inexorably forward through time. Inside a black hole, this relationship flips. The radial direction toward the center becomes time-like, meaning that falling toward the singularity becomes as inevitable as aging. Meanwhile, what we normally think of as time becomes space-like, potentially allowing for closed time-like curves and other exotic phenomena that challenge our understanding of cause and effect. If our universe exists inside such a structure, it could explain some of the deepest mysteries in physics. Dark energy, the mysterious force causing the acceleration of cosmic expansion and comprising approximately 68.3% of the universe's energy density, might not be a fundamental field at all. Instead, it could be a manifestation of our universe's expansion within the curved space-time interior of a black hole. The observed acceleration, which shows that distant supernovae are moving away from us approximately 9% faster than expected in a universe with constant expansion rate, might simply be the natural consequence of our cosmic environment. Dark matter presents another puzzle that this hypothesis might address. Comprising approximately 26.8% of the universe's energy density, dark matter makes itself known only through its gravitational effects. It doesn't interact with electromagnetic radiation, making it invisible to our telescopes, yet its presence is absolutely crucial for explaining how galaxies form and evolve. Galaxy rotation curves show that stars in the outer regions of spiral galaxies move much faster than they should if only visible matter provided the gravitational glue holding them together. Without dark matter, galaxies would fly apart, and the cosmic web of large-scale structure we observe today could never have formed. In the black hole universe model, what we call dark matter might be ordinary matter, existing in the parent universe outside our cosmic event horizon. The gravitational effects of this external matter could influence the behavior of matter and energy within our universe, creating the mysterious gravitational signatures we attribute to dark matter. This would mean that the invisible scaffolding shaping cosmic evolution isn't composed of exotic particles within our space, but rather represents the gravitational influence of ordinary matter in a higher dimensional reality we cannot directly observe. The cosmic web itself, the vast network of filaments connecting galaxy clusters across billions of light years, might reflect the structure of matter distribution in the parent universe. Computer simulations of cosmic evolution require the presence of dark matter to reproduce the observed patterns of galaxy formation, but these same patterns might emerge naturally if our universe's matter distribution is influenced by gravitational fields from the external reality in which our cosmic black hole is embedded. Testing this hypothesis presents enormous challenges. By definition, if we're inside a black hole, we cannot receive information from the parent universe outside the event horizon. Light and other signals from that external reality can never reach us, making direct observation impossible. However, the theory does make some testable predictions about the geometry and evolution of our universe that could potentially be verified or falsified through careful observation. One prediction involves the ultimate fate of cosmic expansion. In traditional cosmology, the expansion of space will eventually stretch the universe so thin that star formation ceases, existing stars burn out, and the cosmos enters a long, cold death, lasting trillions upon trillions of years. In the black hole model, expansion might eventually slow or even reverse as the interior approaches some form of equilibrium, potentially leading to a very different cosmic destiny. The cosmic microwave background radiation offers another potential testing ground. The nearly perfect blackbody spectrum of this radiation, with its temperature of 2.725 Kelvin and tiny anisotropies, measured to incredible precision by satellites like Planck, contains a wealth of information about the early universe. The black hole model predicts specific patterns in these temperature fluctuations that differ subtly from those expected in traditional inflation models. Future observations with even more sensitive instruments might be able to distinguish between these competing theories. Gravitational waves provide yet another avenue for investigation. The laser interferometer, Gravitational Wave Observatory, has already detected dozens of gravitational wave events, mostly from merging black holes and neutron stars. The most massive black hole merger detected so far involved objects of approximately 85 and 66 solar masses, creating a final black hole of approximately 121 solar masses whole of about 142 solar masses and releasing energy equivalent to about 8 solar masses in gravitational waves over a fraction of a second. These ripples in spacetime carry information about the fundamental properties of gravity and the structure of the universe itself. If our universe exists within a black hole, it might occasionally interact with other structures in the parent universe, creating distinctive gravitational wave signatures that could potentially be detected by future instruments. The proposed laser interferometer space antenna, scheduled for launch in the 20s, will be sensitive to much lower frequency gravitational waves that could carry information about cosmic scale phenomena invisible to ground-based detectors. The philosophical implications of this scenario are equally profound. If true, it would mean that every human being who has ever lived, all 8 billion people currently inhabiting Earth, and the estimated 117 billion humans who have lived throughout history, exist within a cosmic structure that defies our most basic intuitions about reality. The pale blue dot that Carl Sagan so eloquently described, suspended in a sunbeam and containing all of human history, would itself be suspended within something incomparably vaster and stranger. This perspective might fundamentally change how we think about our place in the cosmos. The anthropic principle, which suggests that the universe's physical constants are fine-tuned for the existence of life, takes on new meaning if our universe is just one of countless others embedded within black holes throughout a vast multidimensional reality. The precise value of the fine structure constant at approximately 1/137, the exact mass of the proton at 1.672 times 10 to the negative 27 kilograms, and the specific strength of the nuclear forces that allow stars to shine and heavy elements to form through nucleosynthesis. All of these might be environmental conditions specific to our particular cosmic environment, rather than fundamental features of reality itself. In other cosmic black holes, physical laws might operate differently, creating universes where stars cannot form, where atoms remain unstable, or where the expansion rate prevents galaxies from condensing out of the primordial hydrogen and helium left over from Big Bang nuclear synthesis. Only in those rare cosmic environments with the right combination of physical constants would complex chemistry, stellar evolution, planetary formation, and eventually biology become possible. This raises the tantalizing possibility that life might be far more common across the full multidimensional cosmos than we currently imagine. While our own universe contains at least 2 trillion galaxies, each potentially harboring billions of habitable worlds, the total number of life-bearing planets across all nested realities could be essentially infinite. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy by considering factors like star formation rate, the fraction of stars with planets, and the likelihood of life developing, might need to be expanded to encompass the vast hierarchy of nested universes. The search for extraterrestrial intelligence takes on cosmic proportions in this scenario. The signals we're searching for with projects like Breakthrough Listen, scanning millions of stars across multiple galaxies for signs of technological civilizations, might represent just the faintest whisper of intelligence across a cosmos teeming with life at every level of reality. The famous Fermi paradox, which asks why we haven't detected obvious signs of alien civilizations despite the vast age and size of the universe, might be resolved not by the absence of life, but by the impossibility of communication across the event horizons separating different levels of cosmic reality. Recent discoveries have added new dimensions to these speculations. The James Webb Space Telescope has revealed galaxies that formed much earlier than previously thought possible, existing just 400 million years ago, years after the Big Bang when the universe was only 3% of its current age. These ancient galaxies appear surprisingly massive and mature, challenging our understanding of how quickly cosmic structures can evolve. Some of these early galaxies contain supermassive black holes, with masses exceeding 1 billion times that of the Sun, somehow growing to enormous size in the brief time available since the beginning of cosmic history. In the black hole universe model, these observations might make more sense. If our universe's expansion represents the interior dynamics of a black hole in a parent cosmos, The apparent youth and rapid evolution of early galaxies might reflect initial conditions established during the collapse process that created our cosmic home. The matter and energy that fell into our parent black hole might have carried with it organizational structures and physical processes that allowed for accelerated galaxy formation in the early epochs of our cosmic history. Quantum mechanics adds another layer of complexity to this picture. The information paradox, which asks what happens to quantum information when it falls into a black hole, becomes even more perplexing if we ourselves exist within such a structure. Stephen Hawking's discovery that black holes emit radiation and eventually evaporate raises questions about the ultimate fate of any universe contained within. A black hole with the mass of our observable universe would take an unimaginably long time to evaporate through Hawking radiation, approximately 10 to the 100th power years, a timescale that makes the current age of the universe seem like less than an instant. However, quantum effects at the event horizon might create connections between our universe and the parent reality that transcend classical general relativity. Quantum entanglement between particles inside and outside the event horizon could create what physicists call Einstein-Rosen bridges or wormholes, shortcuts through spacetime that might allow information or even matter to flow between different levels of cosmic reality. These quantum tunnels might be so rare and unstable that they have no practical effect on cosmic evolution, or they might play crucial roles in connecting the nested hierarchy of universes in ways we're only beginning to imagine. The holographic principle adds yet another twist to this cosmic story. This principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. If our universe is indeed the interior of a black hole, then all the information describing every atom, every star, every galaxy, and every moment in cosmic history might be encoded on the event horizon surface surrounding us. A sphere with a radius of approximately 46.5 billion light-years and a surface area of roughly 10 to the 123rd square meters. This would mean that what we experience as three-dimensional reality might actually be a projection from information stored on this cosmic boundary. Every sunrise witnessed from Earth, every supernova explosion observed in distant galaxies, every chemical reaction occurring in living cells, every thought passing through human consciousness. All of it might be emergent phenomena arising from information processing on a two-dimensional cosmic hologram. The implications for our understanding of consciousness and free will are staggering. If our thoughts and actions are encoded as information on a cosmic boundary, what does this mean for human agency and moral responsibility? Are we truly making choices, or are we simply experiencing the unfolding of a predetermined information pattern written into the structure of space-time itself? These questions push us to the very limits of scientific inquiry, where physics begins to merge with philosophy and metaphysics. As we contemplate these mind-expanding possibilities, it's important to remember that science progresses through careful observation, rigorous experimentation, and mathematical analysis rather than pure speculation. The black hole universe hypothesis remains highly speculative, lacking definitive observational evidence that would elevate it from interesting possibility to established theory. Many physicists remain skeptical, pointing out that the similarities between black hole interiors and expanding universes might be mathematical coincidences rather than signs of deep physical connection. Alternative theories continue to compete for our attention and research resources. Eternal inflation suggests that our observable universe is just one bubble in an ever-expanding cosmic foam, with new universe bubbles constantly forming through quantum fluctuations in a higher dimensional inflationary field. String theory proposes that reality consists of 11-dimensional brains floating in an even higher dimensional space, with our familiar 4-dimensional spacetime representing just one slice of this vast multi-dimensional arena. Loop quantum gravity offers yet another perspective, suggesting that space and time are not continuous, but instead consist of discrete, quantized units at the smallest scales. In this view, the Big Bang singularity might not represent the beginning of time, but rather a quantum bounce from a previous contracting phase, creating an eternally cycling cosmos with no ultimate beginning or end. Each of these theories makes different predictions about observable phenomena, from the polarization patterns in cosmic microwave background radiation to the distribution of gravitational waves across different frequency ranges. Future observations will help determine which, if any, of these competing models best describes the reality we inhabit. Regardless of which theory ultimately proves correct, the very fact that we can contemplate such profound questions about the nature of reality represents one of the most remarkable achievements of human civilization. In just a few centuries, we've progressed from thinking Earth was the center of the universe to contemplating the possibility that our entire cosmos might be embedded within structures so vast and complex that they challenge the very limits of human comprehension. The story of cosmic discovery continues to unfold with each new observation, each theoretical breakthrough, and each technological advance that extends our reach deeper into space and further back in time. Whether we ultimately find ourselves living within a black hole, floating on a multi-dimensional brain, or inhabiting some other exotic cosmic structure we haven't yet imagined, the journey of discovery itself transforms our understanding of what it means to exist in this strange and wonderful universe we call home.